Let's see one of the application of first order ordinary differential equation, and look at it in the concept of something called growth and decay problems. Basically, this is needed in order to do what is called population estimation. We use to estimate population in a futuristic date, usually, anyways. Right, that's one. Also use it for census. Right, so it's basically an application of maths into real life problems. So if you give me a bit of data, if I get a bit of data, I can forecast what a population would look like in years to come. Hopefully, all conditions stays the same. All right. So basically, that's now the concept of the application of this into growth and decay. Let me give you something to note, and then we can start. Take that, please. This involves the prediction of the size of any population. This involves the prediction of the size of any population at any time, comma, t, full stop. T, time, small t, full stop. Usually, the rate of growth of a population, of size x is directly proportional to the size. Is directly proportional to the size. Is directly proportional to the size. So basically, this small English I just spoke is what you need to solve problems that involves application of first order differential equation to growth, right? The simple concept is that the rate of increase or decrease, we look at it in terms of increase and in terms of decrease. But the simple concept is that the rate of change of the population is directly proportional to what there? The size itself. Now, first things first, look at your notes. When I said size, which alphabet did I use to represent size? X. If I say the rate of growth, how do you express rate in terms of mathematics? When you say rate, what comes to mind? When we say rate, what comes to mind? Let's use velocity. What is velocity? The rate of what there? Change of what there? Distance. So because what there? Distance all over what there? Time. All the what there? ds dt. So if I say the rate of growth of a population becomes what there? Dx dt. Right. Usually the rate of change of the size, this is directly proportional to what there? The size itself. That becomes x. That becomes x. All right, so we have this. If I have a proportionality sign in mass, what do? Take off the sign and put what there? An equal to, and what again there? A constant. Take off this man here, put equal to, put constant. I have that the x, the t, is equal to my constant k, and then what here? X. I have this. With this now, or given this equation here, we can solve this using what there? Variable separable method. Right? Take x with the x, take the t with x. So look up and watch this. This one is coming down, this is going up. It is mathematically correct. So I'm saying this. I have the x all over x is equal to, this one goes up because what there? K dt. These two, is it correct, please? Please confirm, is it correct? Yes. X comes down here, this, the t goes this way, right? So have this. What's my next task there? I'm integrating. So, integrating, if I integrate, what do I have there? The integral of the x over x is equal to the integral of what there? K dt. All right. This one here is same as what there? Integral of what? 1 over x dx. That's this. 1 over x dx is equal to integral of k with respect to t dt. Please, let's get this. Let's get this. If I integrate 1 over x, what do I get there? Ln x. So I have ln x is equal to, integrate this one here. What do you get? Kt. You can look at, if you're not sure, you can look at it this way. If we say the integral of k dt, in this concept here, k is a constant. Take it outside integral sign, it becomes k integral of dt. We said integral cancels what there? Differential. What do you have there? Kt. All right. This gives you kt plus c, your constant of integration. How do we solve this? What do we do? How do you get x here? What do you do? If ln x equal to this, how do I get x? What do I do? Take exponential of both sides. So exponential of this ln x is equal to exponential of this kt plus c. Please observe this. We've handled this one in previous classes. Where if we have exponential raised to ln, what happens there? This one comes down. So you have that. From here, we have that x is equal to what there? Exponential kt plus c. There is something we know about the addition of parts. We say a to power m multiplying a to power n is equal to a to power add them m plus n. Please, it's m plus n, not mt, as most of you see mt in here. It's m plus n, please, right? So I have this. In essence, look up, please. In essence, if I have powers adding, I can expand it to be the same base they are multiplying. So please watch this. Watch this. This will be equal to, they are adding, so it becomes exponential kt multiplying exponential what there? C. You have this. So we are here. At this juncture, let's do something else. What else can we get? Let's use one alphabet to represent this. So I'll say let A be equal to what I have here, exponential C. What do you have there? You have that x is equal to this one here, exponential kt multiplying what there? A. Let A be this. So if I multiply, what do I have here? X is equal to what there? A exponential what there? Kt. Basically, this is the equation we need for population. X equal to A exponential Kt. We have this. This is the equation we need for this, right? Let me add a bit of a tweak to this. Just tweak just for your information. What we just did here is for growth. It's a two-way thing. It's either the population is growing or it's what there? Decreasing or reducing. What I have here is if the population is growing, you'd have this. If you're solving the same problem and you're seeing the terms decay, if the population is decaying, what happens? It is what there? Reducing. So this is the equation if the population is growing. What if it is reducing? What do you do? Simple concept. It's the same thing, but I will introduce a negative. Why the negative? Well, the size is what there? Reducing. In essence, for decay, you have minus, not this point, minus, 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 and minus. So for decay or a reduction in population, you have that x is equal to a exponential minus kt. No big deal. The same thing. So it's positive if there's a growth or an increase in population. It's negative kt if there's a reduction or a decay of the population. Before we take examples, some few things to note. Let's define terms. Where x is equal to population size, just to be clear, by population size we mean population number. Okay, and t is time. This is not physics where you say time should be in seconds. In some cases, this time could be in seconds, could be in minutes, could be in hours, could be in years, could be in decades, as the question suggests. So you have to really understand. And A and K, are constants. Found using conditions in the question. Conditions in the question. All right, so we have this. Okay, so we have this basically. Okay. So copy down. Let's take some examples, please. Sample question one. Sample question one says a bacterial culture. That's what do you call it? A group of bacteria, right? Yeah. A bacterial culture was initially 500 bacteria and grows at the rate proportional to the size of the bacteria present. Full stop. After 3 hours, there are 8,000 bacteria. Full stop. A says find an expression for the number of bacteria at any time t. B says find the number of bacteria after 4 hours. C says when will the population reach 30,000? That's the C part. So how do we solve this? Basically, when they say find an expression for this, you are technically supposed to derive the equation. So solution A, when they say find an expression for this, you are technically expected to derive what there? The equation. How do we solve this? So look up. Let's do the first one there. Find an expression for the number of bacteria at any time t. Look up, please. We said earlier that the rate of growth is what there? Directly proportional to what there? The size. And this is there in your question. If you look at the question, it said, and grows at the rate proportional to what there? The size. They said it grows. What does that mean there? An increase in population. So I'm using positive x here. Let's continue with this. This becomes the x, the t is equal to kx. We have this. I'll be a bit faster with this because we've done this already. So I'll have what here? The x all over x is equal to what there? K dt. So what do you have here? This gives you ln x is equal to what there? Kt plus c. From here, we say you have what there? X is equal to what there? Exponential kt plus c. We've already done this before now, please. All right, so this is equal to exponential kt multiplying exponential c. And we said exponential c should be equal to what there? A. So x will now be equal to what there? This becomes a. That's a exponential what there? Kt. We've done this already in full. So let me save your time. Now, this is more like a vague expression. At this point, now we have to impute values. What do I mean by that? Look at this, please. Listen to the term that they said a bacterial culture was initially how many bacteria there? How many there? 500. Now listen. When you hear the term initially, The term initially means at t equal to 0. That's the meaning of the term initially. So it means that at t equal to 0, this is the meaning of initially. They said the number of bacteria x is equal to what there? 800. 500, 500 please, sorry. It's equal to 500. Now impute values. What do you have there? X 500 is equal to a exponential k into t. What's t there? Initially, that's 0. Let me simplify this side. This is equal to a exponential k times 0 is what there? 0. You have this. Exponential 0 is what there? 1. This is 1. 1 times a is what there? A. What does it mean here? 500 equal to a. That means what there? A equal to what there? 500. They said where the value of a and k are got using conditions. With the first condition, I've got the value for what there? A. All right, so look up, please. So with this, we've gotten the value of A as 500. All right, so, and that's why we said the value of A and K are got using what there? Conditions in what? The question. We've used the first condition, what we said initially. So at when we say initially, T is 0, we said the population size was what there? 500. Now, originally they said after 3 hours. Now, if you look at after the 3 hours there, the first thing you want to do is that if you observe, if I scan to the question there, in the B part, they said, find the number of bacteria after what there? 4 hours. They mentioned hours in the question, they mentioned hours in B. That means the time is in what there? Hours. In some questions, you could see B now says, find the number of bacteria after 2 days. You're now computing between what there? Hours and days. In 2 days, how many hours do you have there? 48 hours. So if they say find the number of population after 2 days, you take T as what there? 48, not 2. Because you're working with what there? Hours. So please know how this works. Alright, the big part they said after 3 hours, so T equal to 3, they said the population X is equal to what there? 8,000. Alright, let's impute values here. From this, we can say that X is equal to A. The value of A is 500 exponential kt. Let's impute this condition. X is 8,000, so 8,000, that's X, is equal to 500 exponential k into when t is 3. That's 3 here. To solve this, first things first, I'll have to divide this by 500, divide this by 500. This cancels this. This gives you what there? 16. 16 is equal to exponential k times 3 is 3k. How do you get k here? My next task here is to take ln of both sides. So it becomes ln of 16 is equal to ln of what I have here, exponential 3k. So I have ln 16 is equal to, if I take ln exponential anything, the answer becomes that thing there, 3k. I have this. To get k, divide both sides by 3. So from here, let me get this. So ln 16, this it's equal to 3k. Divide here by 3, divide here by 3. This cancels this. K is equal to, give me your answer in 4dp. What do you have? 0.9242. That's the value of k. Let's input this back into this equation here, this one here. We'll have that x, so x is equal to 500 exponential kt. What's k there? 0.9242 kt. I would advise that you always use k word there for decimal places. Why? The number of decimal places you use, the more accurate your result becomes. This is what you learn under error analysis in what is called numerical analysis. What you should have been doing now is actually numerical analysis. You would have learned this concept that the more the number of decimal places you use, the more accurate your answer becomes. And that's why, this explains why when you are learning science in basic school, from those your primary 5, they will say take G as equal to what there? 10 meter per second squared. 10 was not the value. What's the value there? 9.8. As you go higher, they now say, don't use 10. Use what there? 9.8. Why? More decimal. This was converted to what there? A whole number. As you now go higher to SS3, they will say G is equal to what there? 9.81. Look at this. That's why. So the more the number of decimal places what there, the more accurate your result is. So this will give you a much more accurate result than this. But they are approximately the same thing now. Well, that's baby science. When you're doing stuff that needs precision, you can't be making this error. So that's the concept. So that's why I advise you what there, 4 decimal. Instead of saying 0.92, use 9242. 4 is good enough. Right? So I believe I've explained this concept. So that's the A part done. What's the B part there? Find the number of bacteria after 4 hours. That shouldn't be a problem. B, at T equal to 4. Of course, we're still working with hours. Find X. That means X will simply be equal to 500 exponential 0.9242 times what there? 4. Let me believe you can give me your answer here. So give me final answer. X equal to what? Give me final answer. Just punch it. What's your final answer? 20159 0, hold on, 03 point 03 99. No, don't use 04. Oh, don't stress. 4 decimal places is what you're working with this one now, not here. So 04. So that's my answer. So this is good. 20,100 and what there? 59. All right, that's fine. So that's it. So this one is easier now, not that Bernoulli, right? Bernoulli is just crazy. This one is easier. Now I'm telling you now. This one, once you get your equation, just substitute. It's easy. Not Bernoulli. Bernoulli is just crazy. What's the C part? When will the population reach what there? 30,000. Basically, they give you the value of what there? X. You have to find what there? C. So, at X equal to 30,000, C, when? Talking about time. C is unknown. So, bring it here. What do I have here? X, 30,000. 30,000 is equal to 500. So, 500 exponential kt. K, that's 0.9242 t. Let's get the value of t here, please. To get t here, my first task would be divide here by 500. Divide here by 500. This will cancel this. It's off. This will give you 600. This will give you 60, please. 60. 60 is equal to exponential 0.9242 t. I want to get the value of t. What do? Take ln of both sides. Ln. So ln of 60 is equal to ln of exponential 0.9242 t. From here, we said ln will cancel exponential, leaving you with this. So ln of 60 is equal to 0.9242 t. To get t now becomes a walkover. All right, from here, ln 60 all over 0.9242 is equal to 0.9242 times t all over 0.9242. All right, so basically the concept is just divide both sides by the coefficient of t. So with that, this will cancel this, can now get t. So t is equal to, please give me this value, please. 4.43 in hours, right? The hours, the value there is 4.43 hours. So this is how long it will take the bacterial population to get to 30,000. So that's your answer, please. All right, let's look at yet another question.
Get more by joining our Differential Equations channel membership or visit www.joniemanual.com/courses and get the Differential Equations Made Easy course. Both links in video description. Get more by joining our Differential Equations channel membership or visit www.joniemanual.com/courses and get the Differential Equations Made Easy course. Both links in video description.